Hello students, and welcome to this lesson on geometric probability. Today we will be calculating geometric probability of simple shapes and number lines using our journal notes and examples. Alright, so what is geometric probability? Well, a geometric probability is just a probability that we're expressing as kind of a picture instead of just numbers. So, one of the things that we can define here is that geometric probability is where points on a segment or a region of a plane represent the outcome. So it's where points on a line segment or plane represent the outcomes. And what it's going to be represented by is, or how we're going to calculate it, is we're going to take the ratio of the two lengths or the two areas. So it's found by the ratio Alright, so let's talk about probability and length. So if I want to find the probability that point S, so S is just some outcome. So this is just like when we're asking about any outcome in theoretical probability of just numbers. So the probability that S is on BC. Alright, so if I'm going to talk about the point S being on BC, I would say probability. Remember, this is going to be our probability symbol. Whenever I write P, I'm meaning probability. So we're talking about the probability of a specific event. And in this case, our specific event is S on BC. And what we would do, if this is our entire set, so we've got the entire segment AD. So that's our whole universe right there. And the area that we actually desire is B to C. So the probability that if we choose a random point on AD, that is on the length BC will be the length of BC divided by the length of AD. So really the main thing that we have to take away from this is that representing probabilities as lengths and areas just allows us to have a more complete picture of what those probabilities will be. We can also talk about probabilities on areas. So if we're talking about the probability that some point S is on the region N, so this is the probability that if I take some random point here and it's in, I want to find the probability that S here is in the region N. Well, it's pretty simple what we need to do. So we have P that S is in region N, and all that will be is that the area of N divided by the area of R. So we always assume that S will be in R no matter what. So S has to be within this region, but we're trying to find out if it's inside of the subregion of N. And if you need to remind yourself of our formulas for a rectangle, it's right here, and our formula for a triangle is right here as far as areas go. These are pretty basic. So, what if we have the opposite? What if we have some shaded region, which is the larger region, and some non-shaded region, which is the smaller inner region? So we're going to call this region R again, and this region N again. All right, so if I want to find the area, if I want to find the probability that it falls within this larger shaded area, then my first step is that I'm going to be finding the area of the larger object. Then we're going to find the area of the smaller object. And then finally, this is just like when we were doing our complements, right? It is not in the triangular region. So we're going to say the area minus the area of the small, and that's going to be the area of the shaded region. Right? It's as if we cut out this triangle from the square. All right, and finally, the probability of that shaded region will be the area shaded divided by the area of the square, because that's the entire region. The square represents the entire set. So let's look at a couple of examples for our length. So in example 1, we're talking about the probability that a point will fall on QR given that it is within the line segment ST. So we have S, which is at 2, Q, which is at 5, R, which is at 8, and T, which is at 14. So what I can determine is that QR itself is equal to 3 in length. ST is equal to 12. So if I'm trying to find the probability that it lies on QR, I'm just going to say 3 over 12 or 1 over 4. Or I could state this as 25% of the time I'm going to fall on QR. Let's look at how this looks in a word problem. So, a train runs every 25 minutes. Find the probability that you will have to wait at least 10 minutes for the train. So, we can think of this in two ways. You can either think of this as you are waiting at least 10 minutes, so that's 15 minutes and greater, right? Had to make a quick correction here. So, we're talking about this train that is coming every 25 minutes. So it starts at 0 when the train leaves, and then what we're trying to find out is the probability that you're going to have to wait at least 10 minutes for the train. So if we're waiting at least 10 minutes, then we're talking about everything which is greater. So if the train comes every 25 minutes, then what we're talking about is the length between having to wait 10 minutes and the train arriving. So the length here will be 15. So if you arrive 10 minutes before the train leaves, then you're waiting less than 10 minutes. So if you arrive before then you're waiting more than 10 minutes for the train to arrive. So the only thing that we care about is that 10 mark. So the probability that your wait time is greater than or equal to 10 is going to be, well, it's all of the other minutes. So if you arrive 10 minutes before the train gets there, you're waiting 10 minutes. But every point before then could possibly be more than 10 minutes. So we're saying 15 over 25, or 3 over 5, or 60%. So if you are randomly arriving within this interval, then there is a 60% chance that you're going to wait more than 10 minutes for the train. All right, and let's run through some probability and area examples. So for area, it's a little bit different, but still pretty similar. It's actually, I think that area is a little bit easier to grasp than the line segments. So if we're talking about the probability that we fall within the shaded region, the shaded region is this one right here. So this is our shaded region. And we want the probability that we fall within it, given that we have to stay within the larger square region. So, what is this probability going to be? Okay, so we know that it's going to be the area of the shaded region divided by the area of the larger region. So, we just have to calculate the areas. So, our triangle, the area is 1/2 times 4 times 5, and that's equal to 10. And we also have our rectangle, and our rectangle is 5 times 8, and that's 40. So the probability that we fall within the shaded region is going to be 10 out of 40, but I could also write this as 1/4 or 25%. All right, and now we've got a cutout problem again. So, I'm looking for the probability that we fall within the shaded region. Well, again, we need to find the area that we desire and divide it by the area of the total. So, we have our large square, and this is our shaded region that we want. So we have our large square, and that's going to be 6 times 6. Then we have our small square, and that's going to be 2 times 2. So this is 36, and this is 4. So my shaded region is actually 36 minus 4, right? Because I have this cutout here. So that's going to be 32. So the probability that I fall within my shaded region is going to be 32 out of 36, which can be reduced to 8 over 9, or 89%. So our assignment for today is that you need to pick up the geometric probability practice time, and then we also need to work on our Tuesday homework. And what I want to leave you with is think about the advantages and disadvantages of working with an area. What situations might call for geometric probability? Why do we need to use it? Until next time, I'll see you later. Goodbye.